Hello friends, this is a video, Ben Marlin, looking at a video once again of stuff for our Calc 3 class. The topic for today is looking at the idea of the convergence of series. We talked about the convergence of sequences previously, and essentially all you have to do to determine whether a sequence converges is to take the limit of the terms, and if the limit exists, the sequence converges to that limit. That was related a little bit to the idea of a horizontal asymptote, okay? And generally, you often need to know something about, something about L'Hopital's rule to get some of them figured out, okay? So today's topic, we're looking at the idea of a series. And so let me share screen with you here to show you what.
Hello.
Shut up, Siri. That's going to be super convenient there. So I have an example written down here where we have terms a sub n, and we are looking at the convergence of a series. Now, a series in general would be written down to say something like summation n equals 1 to infinity of that 2n squared minus 3n plus 1 divided by 3n squared plus 4n plus 7. And so what you're being asked to determine is whether that series, that summation, converges to something that's finite. So this means that what you want is not to take the limit of the terms a sub n here, but rather if you took the sequence of partial sums at s sub n and talked about them. So you might also think about this as going and plugging in the n equals 1, n equals 2, and so forth. So if I plugged in n equals 1 to this a sub n here to get the first term, across the top it would be 2 minus 3 plus 1. So you would end up with a 0 across the top. And on the bottom, you would end up with 14. So that would mean that you really have 0 over 14 there. And then if you plug in n equals 2, you would get, let's see, 8 minus 6, so 3 on the top, and on the bottom you would get, let's see, 12 plus 8 is 27 plus, and then you could plug in n equals 2, n equals 3, n equals 4, etc. And of course, there's no way that you can actually find this sum by adding up an infinite number of things, because you're a finite being. So if you were asked in an example like this to look at that thing there and determine whether or not it converges, the way that you would do that this time is to take and look the limit as n goes to infinity of the a sub n's, and you can see that that would be 2/3, right? And if you actually wanted to have the limit as n goes to infinity of the s sub n's not be infinite, so being finite, that would mean that your actual terms that you have need to go to 0. So anytime that you can find out that the limit of the terms goes to something other than 0, then you can automatically say that your summation n equals 1 to infinity of that a sub n diverges, just because of the fact you're adding up infinitely many things and the things are not going down towards 0. All right. So if you actually look, though, at the definition of convergence of series, what it's really about is that sequence of partial sums. So you have the question of whether your sequence of partial sums converges. And so if you were given an expression for the S sub n directly, then you wouldn't have to do anything with finding out the A sub n's. You wouldn't have to find the terms. So for example here, if I were to simply say to you on this that the S sub n was equal to, I don't know, maybe something like n squared minus 3n plus 1 divided by 2n squared plus n, then in order to find whether this converges or not, you wouldn't have to find out the a sub n. You would simply say limit as n goes to infinity of n squared minus 3n plus 1 over 2n squared plus n. The terms on the top and the bottom have the same growth rate. They're both n squared. So you can just divide leading coefficients and get 1/2 out of it. And that means that the series that you don't even know what the a sub n's are converges, because the sequence of partial sums converges, and that's what the definition of convergence is. Now, the situation that we're going to be in generally is that we will know the sequence of terms, but not the sequence of partial sums. What we're going to look at today really is the exceptional sort of case where you actually do know some expression for your sequence of partial sums. So a good example to look at on this is something that's referred to as a geometric series. So if I do something like this, summation n equals 0 to infinity, and I'm going to put 3/4 times, let's say 2/3, and the 2/3 I'm going to put to the n power here, okay? That would be, if you plug in n equals 0, you have 3/4 times 2/3 to the 0, so it's times 1. But then plus, plug in n equals 1, and you have 3/4 times 2/3, and that gives you 1/2. And then when you plug in n equals 2, you'll have 3/4 times 4/9, and so you end up with 1/3 out of that. And then when you plug in n equals 3, man, I'm going to have to jot these down as I go to keep track. So when I plug in n equals 3, I've got 3/4 times 8/27, which will give me some cancellation here, and I would have 2/9 coming out of it. So, and recognize I can keep going like that forever, you know, not forever, but as long as I feel like going. And I can get a pretty good approximation by, running out 1,000 terms or something. And if you're doing this with the computer, hell, let it do 1,000 terms. But what we really need to know is whether or not it converges, because if it doesn't converge, having the computer work on it is kind of a waste of effort. So what we're going to have to do on this is to be a little bit more generic in order to see what's going on. So a geometric series will always have some constant at the front, and I'll refer to it as A. And if there isn't such a term, then you just take it as being 1. And then we use R for ratio because we're always talking about a fraction, and that's to the nth power. So that would be that we would have, excuse me, A plus AR plus AR squared plus AR cubed plus ... And it continues forever. Your sequence of partial sums then, Sn, would go A plus AR plus on up to AR to the nth power. Okay? Now, the reason that I write this out is that I have a slick trick. If I multiply this whole thing by 1 minus R, it doesn't do anything on the left-hand side. But on the right-hand side, you have A plus AR squared plus ... plus AR to the n minus, and multiply that whole thing by R, and you have AR and minus AR squared and minus AR to the n, and one more term of AR to the n plus 1. And so you get all kinds of cancellation going there. And that means that 1 minus R Sn is going to be A, I'm going to factor that out, 1 minus R to the n plus 1. So Sn will be A 1 minus R to the n plus 1 over 1 minus R. So if you have so that its absolute value is less than 1, then the limit as n goes to infinity of R to the n plus 1 is going to be 0. And that means that your limit for your S of n would end up being A divided by 1 minus R. So returning to this example where we had, oh, as a matter of fact, I'm going to do this. I'm going to do a slightly different example. Sorry. If I had here maybe 2/3 plus, let's say with this we want to have just 2/9 and 2/27 and 2/81 and so forth like that, then we should be able to see that that is really 2/3 times 1/3 to the n that we need to add up here. Summation n equals 0 to infinity. Remember that that A will always be whatever that first term is, and then the R is what you're multiplying by each time. And so this one, because the absolute value of your R is 1/3, which is less than 1, then you're going to get 2/3 over 1 minus 1/3. So 2/3 over 2/3, which is 1. So if you get a geometric series, you decide whether or not it converges by just looking at the absolute value of that ratio. If it's less than 1, boom, you're done. So that determines convergence. And you can actually see what it is it converges to. Now, on the other hand, if you have most series that you might be dealing with, you may not be able to get an Sn, okay? Let me give you one more example here where we actually can get a term for the Sn's. And so I'm going to share screen again. And the thing I'm going to deal with, I'm going to write Bn And it's going to be 1 over 2n plus 1 minus 1 over 2n plus 3. So that if you wrote out your first partial sum here, you would have 1/3 minus 1/5. But if you wrote out your second partial sum, it would be 1/3 minus 1/5 plus 1/5 minus 1/7. And you cancel those. Then your third partial sum, you'd have 1/3 minus 1/5 plus 1/5 minus 1/7 plus 1/7 minus 1/9. You can see that we get a cancellation on the adjacent terms there. And so, whereas the first time you had 1/3 minus 1/7, and I can't do the arithmetic in my head, I'm ashamed to say, the next one would have been 1/3 minus 1/9, which I actually can do the arithmetic in my head this time. So in a more general way, your Sn is going to have this 1 over 2n plus 1 minus 1 over 2n plus 3 plus, and I am going to be a little bit lazy with this and try to just write the last two terms. So the last term of it would have the n in it, 2n plus 1 minus 1 over 2n plus 3. The next to last term we know would have the 1 over 2n plus 1 as a minus. And it may take some thinking, but if you substitute in n minus 1 where there's an n, you will end up with 2n minus 1 here. And naturally, I goofed up what I was writing. So if you spotted that, give yourself an extra point for being clever, but take one away from me for not catching it. But you're canceling terms just like you are in the example there, but there's a lot of terms that are getting canceled in the middle that we just never see. So our Sn on this one will turn out to be 1/3 minus 1 over 2n plus 3. And that means that in this case, we can actually take a limit as n goes to infinity of the Sn, not the An, the Sn. And when we do that, we will get 1/3. So that tells us that the summation equals 1 to infinity, 1 over 2n plus 1 minus 1 over 2n plus 3 converges. And we even have the nice fact that we can say what it converges to without doing an infinite number of additions there. Okay? So, in general, the problem you run into is that you will have a series that you don't know the Sn for. You know the An. And what most of this chapter is about is trying to find out whether something converges using just the Ans. If you can do that, then once you know it converges, you let a computer approximate it. You know, the problem is that there are series that have hidden stuff going on where they look like they should converge and they don't. The quickest example for that, and this is a little bit of a tease for tomorrow's stuff, the quickest example to see is the summation n equals 1 to infinity 1 over n. That would be 1 plus 1/2 plus 1/3 plus 1/4 plus ... and it would continue on forever. You know that the limit as n goes to infinity of 1 over n equals 0. But this summation n equals 1 to infinity of 1 over n diverges. Okay, and we'll see that with the integral tests and stuff that we'll do in the next video. So Make sure to tune in next time to see what's going on with that.